Hello everyone, welcome back to the Control System Engineering lecture. In the last lecture, we have studied about the introduction to the Bode plot diagram, few transfer function and their magnitude plot construction, semi-log paper, use of semi-log paper, etc. In this lecture, we are going to use some numerical example and see how the Bode plot construction is actually happened. And also we'll study about the stability analysis using a Bode plot construction, gain margin, phase margin, gain crossover frequency, and phase crossover frequency, and their calculation with the help of Bode plot and without the Bode plot. So let's move forward. Before sketching of a Bode plot, let me give you a brief step-by-step instruction for construction of a Bode plot. So the step one in Bode plot construction is to represent your transfer function in the given form, where all the coefficient should come together with the j omega and the other value should be always equals to 1. So it will make easier to plot a construction and also help in simplify your calculation by using a Bode plot construction. Okay, so next step 2, find out the corner frequencies. If you have represented your transfer function in this form, then the corner frequency can be calculated 1 upon z1, 1 upon z2, 1 upon p1, 1 upon p2. Also note that you should identify which frequency is associated with the zero or the poles. Next is step 3. We will do what? We will rearrange these frequencies into ascending order. We will represent the minimum frequency at the left side and the maximum frequency on the right side. So we will represent your frequency in ascending order in the step 3. Step 4, calculating the starting point of Bode plot. See, we know that in the Bode plot construction, we have to find out from where we have to start. So the initial point we can find out if we substitute the value of omega equals to 0 in this transfer function and find out the magnitude of the system at omega equals to 0. So this will provide you the initial point of your Bode plot construction from where you have to start. After calculating the initial value, we will look forward to the find out that if there are any zero or pole exist at your origin or not. If there are any poles and zero exist at your origin, then in case of pole, after the initial point, your magnitude will start decreasing with the rate of minus 20 dB per decade. And if there are multiple pole, then n pole multiplied by 20 dB will be your net slope in case of pole. Similarly, in case of zero, if there are zero exist into your system, then your magnitude will start increasing at the rate of plus 20 dB per decade multiplied by number of zero exist into your system. This slope will continue up to the higher frequency, whatever the higher frequency you have, which lead us to the step 5. So after the zero, after the origin, what is the next higher frequency you have? So up to that higher frequency, the previous slope was continue, and after encountering this particular frequency, we will see that if it is associated with the poles or zero. If this corner frequency is associated with the pole, then it will reduce your net slope with the 20 dB per decade per pole. And if it is associated with the zero, then it will increase the slope of your magnitude with the plus 20 dB per decade. For an example, if initial slope was minus 20 dB per decade, if it encounters any pole frequency, then the slope will be minus 20, minus 40 dB per decade. If initial slope was minus 20 dB per decade and it encounters a zero frequency, then the net slope will be minus 20 plus 20 equals to 0 dB per decade. So 0 will increase the slope and pole will decrease the slope with the rate of 20 dB per decade both. And if there are multiple, so we will multiply the 20 by the number of poles or zeros. So we will repeat this step until we will able to complete all the frequency. We will able to accumulate all the frequencies or not. Then we will see that if there are any complex pole exist into your system or zero exist into your system. If there are any complex pole or zero, we will find out the resonant peak and resonant frequency and complete the magnitude plot construction. So after completing the 6 steps, you will be able to complete your whole magnitude plot. Now, after sketching a magnitude plot, we will sketch the phase plot. For sketching a phase plot, we will use the expression of the phase angle. We will calculate the angle of your transfer function with the help of this expression, and we will draw a table in which there will be a two column. One column will be of the frequency omega, and the other column will be of the phi, angle phi. So we will take a set of value of omega, and we will calculate the value of phi for that particular value of omegas, and we will sketch a phase response. After that, in the step 8, we will check for the two quantities. These are the two main quantities which actually provide you the stability of your system. One is the gain crossover frequency and the phase crossover frequency. With the help of gain crossover frequency and phase crossover frequency, we will find out the value of gain margin and the phase margin. This is the graph. In this graph, you can see that the point gain crossover frequency is the frequency at which the magnitude of your system is 0 dB. Okay. Similarly, the phase crossover frequency is the frequency at which the phase of your system is equals to minus 180 degree. This is will we provide you the gain crossover and phase crossover frequency. I will repeat once again. The gain crossover frequency is the frequency at which the magnitude of the system is 0 dB, and the phase crossover frequency is the frequency at which the phase angle of your system is minus 180 degree. Next quantity, the gain margin. The gain margin is the change in the gain at phase crossover frequency. At phase crossover frequency, what is the value of gain is give you the quantity of the gain margin. Similarly, at the value gain at the frequency, which is the gain crossover frequency, what is the value of phase? And actually distance between this phase and 180 degree minus 180 degree line will provide you the phase margin. Always remember that the gain margin is positive if this difference is below the 0 dB line, and phase margin is positive if it is above this minus 180 degree line. So this will give you the complete analysis of phase margin and the gain margin. So after calculating the gain margin and phase margin, we will be able to comment on the stability, and we'll be able to find out that system is stable, marginally stable, or unstable. For that, please note that the system is called stable if the gain margin and the phase margin both have positive values, and the phase crossover frequency is greater than gain crossover frequency. Similarly, system will be marginally stable if phase margin or gain margin is 0 dB, 0 degree and 0 dB. The system is called unstable if any value between the gain margin and the phase margin is negative, is called the system will be the unstable, or phase crossover frequency is less than the gain crossover frequency. So what is the basic definition of a gain margin? The gain margin provide you the information of the relative stability of your system. It tells you that this much variation in the gain can be allowed before the system going to be unstable. After this particular value of variation, the system will become unstable. So the gain margin in 2 dB means the system will become unstable after the variation of 2 decibels. Similarly, the phase margin will provide you the information about the stability, that your system is stable up to this value of variation in the phase angle. For an example, if 45 degree the phase margin, then the system will be stable up to the 45 degree of variation in the phase angle. Okay. Also note that in this, the gain margin is always measured in decibels. If you are not measuring in decibels, then instead of 0 dB, you can take the value 1 if you are not measuring the gain in form of decibels. So let's take an example. This is the simplest example where your transfer function equals to tan divided by 0.s plus 1. The corner frequency can be easily calculated as omega p equals to 1 upon 0.2, which will give you 5 radian per second. The initial gain, for the finding out the initial gain, we will substitute the value of omega equals to 0, and this will give you the initial gain, which is a 20 dB initial gain. This is the 20 dB initial gain, and after that we will sketch a line up to the next corner frequency. We know that the next corner frequency is 5 radian per second. So we will sketch a line of a 0 dB slope because there is no pole or 0 at the origin. So there will be a constant line with a slope of a 0 dB per decade up to the next corner frequency. The next corner frequency is 5 radian per second. So after this particular frequency, since this frequency is associated with the pole, therefore, the slope of the system will reduce by the minus 20 dB per decade. So after that particular frequency, we will have this, your magnitude will start decreasing at the slope of a minus 20 dB per decade. So this is your construction of your Bode diagram of this transfer magnitude plot of this transfer function. Similarly, you will be able to find out the phase plot by using this expression given in the third point. Phi equals to tan inverse 0.2 omega. Substituting the different value of omega, you can find out the this phase plot given the phase plot. Okay, so after that, we will find out that what is the gain crossover frequency and phase crossover frequency. Note that here we have the magnitude plot crosses a 0 dB line at the frequency of 49.7 radian per second. So at this particular frequency, we will check that what is the value of angle. So the value of angle is something around 84.3 degree, and the difference between this angle and minus 180 degree line will be 180 minus 84.3 degree. So we will have this phase margin 95.7 degree. The difference between this angle and minus 180 degree line, so this will give you an angle of 95.7 degree. So the system will have phase margin of 95.7 degree. Also note that the phase margin will never crosses the minus 180 degree line. So in this case, we are not able to find out the value of phase crossover frequency and the value of gain margin. So since this phase margin is positive and gain, there is no negative gain margin exists, so we can say that the system is stable. Similarly, consider second example. In this example, we have given a transfer function in this form. So we will first rearrange this transfer function in the given form. So this will give you this transfer function given in the first point. And next, we will find out the corner frequency. There is one corner frequency associated with the 0, which is a 1 radian per second. Two corner frequency associated with the pole, 5 and 10 radian per second. So let's see what is the first point in the Bode plot. We will check that after substituting the omega equals to 0 and calculate the gain of the system. When we substitute the value of omega equals to 0, you will have 3 value only left. Then you will calculate in point 3, the initial gain of the system will be the 20 log base 10 omega j0 equals to 9.54 decibels. So let's see how we'll be able to sketch a Bode plot. Since we know that the initial value of gain is 9.54 decibel per second per decibels, so we will start our sketching from that point. And also we know that there is no 0 or pole exists at origin, so there will be an initial slope of the 0 dB per decade. So we will draw a line of 0 dB per decade, which is a straight line parallel to the frequency axis up to the next corner frequency. The next corner frequency is 1 radian per second, which is associated with the 0. Okay. Since the next corner frequency is associated with the 0, therefore the slope of the magnitude will start increasing with the rate of plus 20 dB per decade. Similarly, we will move towards the higher frequency and we will see on the graph that how it will proceed. So check out that the initial slope was coming at the rate of 0 dB per decade, and after encountering a frequency of 1 radian per second, which is the frequency of 0 associated with the 0, then the slope will start increasing with the rate of plus 20 dB per decade. This is the slope of 20 dB plus decade. And after that plus 20 dB per decade, we will see that the next corner frequency, which is 5 radian per second, is associated with the pole. Since the initial slope was plus 20 dB, the pole will reduce this slope by the amount of minus 20 dB. The net slope will be the 0 dB per decade. Similarly, the next corner frequency is 10 radian per second, and since initial slope was 0 dB per decade, now this pole will also reduce this slope of your magnitude with the additional minus 20 dB per decade. So now next magnitude of your slope will be minus 20 dB per decade. So this will complete your asymptotic plot, and you will see that light blue line is your actual frequency response of your system. And this is the Bode plot that you are sketching with the help of asymptotes. So this is quite nearer and approximated to the system, which can help you in find out the stability with the help of minimum calculation with the help of your hand. Okay. So now we will plot a phase response of your system. For plotting your phase response of your system, we will first write down a formula of your phase. The phase phi equals to, you know that all zeros contribute into a positive angle and the all pole will contribute into a negative angle. So tan inverse omega associated with the positive angle minus angles associated with the each and every pole. Okay, so for this we will make a table in which one column will be of frequency which you select, and one column which is a phase which you will calculate with the help of the given formula. So the guideline for taking a frequency omega is totally depend upon you. The soft instruction for guideline of omega is that you have to see that magnitude plot should cross the 0 dB line. So this much frequency you have to take, or at least you have to take up to the maximum frequency, up to the maximum frequency available in your system, which is the 10. So we will take at least 10 times of this frequency. So up to 100 is must necessary, and you can also take the interval between the two consecutive frequency depending upon your intelligence. So this is totally upon you how to plot, how to decide this frequency. So soft guideline is you have to take 10 times of your maximum frequency. So after sketching your phase plot, we will find out what is the phase crossover frequency and gain crossover frequency into your system. So we know that whenever your magnitude crosses your 0 dB line, it's called the gain crossover frequency. And at this frequency, the value of angle is associated with the phase margin. So for calculating the phase margin, what we do, we subtract this angle, which is 84.4 degree from the 180 degree. So this will give you a distance between the minus 180 degree line and this angle. So this will give you the phase margin of your system. The frequency of gain crossover frequency is 150 radian per second. In this example, we can see that there is the phase cannot go beyond the minus 90 degrees. So therefore, there is no phase crossover frequency exist into your system. So therefore, we cannot calculate the gain margin in this case also. So till now, we have measured the gain margin and phase margin with the help of Bode plot diagram. If someone asks you or you have to measure the gain margin and phase margin only, so you can also measure the gain and phase margin without even plotting your Bode plot diagram. So this, in the current slide, we are going to discuss about how to calculate gain and the phase margin of your system without actually drawing the Bode plot diagram. So we know that the gain margin of your system is equals to 1 upon gain of your system at the frequency of the phase crossover. And the phase crossover frequency is the frequency at which the phase of your system is equals to minus 180 degree. So the formula of angle g omega equals to minus 180 degree will provide you the frequency omega pc If you solve this equation, you will have the value of omega pc. Then after calculating the value of omega pc, you will substitute that value into your magnitude and you find out the value of gain margin. So gain margin formula is equals to 1 upon magnitude of your system. Similarly, we know that for a phase margin is calculated 180 plus whatever the angle you have in your system at frequency of gain crossover frequency. So gain crossover frequency is calculated when the gain of your system is 0 dB. If you are not measuring into a dB, then we can say that gain of your system should be equals to 1. If you solve this equation, mod of g j omega equals to 1, then you will be able to find out the value of gain crossover frequency and substitute that value of gain crossover frequency in the phase margin formula, and you will have the phase margin of the system without actually just plotting a Bode plot. So let's take an example, which is the first example. In this we have this transfer function. Let's substitute the magnitude condition. The magnitude should equals to 0 will provide you the gain crossover frequency. So when you substitute magnitude equals to 1 and find out the value of omega gc, this will give you the gain crossover frequency. Solve with this equation and at this frequency we will calibrate the phase of your system and the phase margin of your system. The phase margin of your system will be 180 plus angle of g j omega at omega equals to gc. So which will be equals to 95.7 degree, which we have measured in the first example while we are sketching a Bode plot. Similarly, for the gain margin, we can see that when we solve this angle condition, we will have omega equals to 0. But omega equals to 0 cannot be true because at omega equals to 0, the angle is 0 degree. So in this case, the maximum angle is 0 degree, and when we substitute the value of omega equals to infinite, then the minimum angle will be minus 90 degrees. So the angle cannot approach to the minus 180 degree. Therefore, we cannot conclude that the omega is a phase crossover frequency. So in this case, we cannot find out the phase crossover frequency and gain margin. So let's take another transfer function, which is tan upon s plus 2 s plus 4. Calculate the phase crossover frequency first. We are calculating first gain margin. So for the gain margin, we require the phase crossover frequency, and phase crossover frequency is measured by substituting the angle of system is equals to minus 180 degrees. So let's take this formula of your system, substituting the angle of your system equals to minus 180 degree, and we will have omega pc, which is the phase crossover frequency, is equals to 2.83 radian per second. At this particular frequency, we will calculate the gain margin of your system. The gain margin of your system in terms of decibel can be represented by 20 log base 10 1 upon mod of g j omega, which is actually represented in this form, which is inverse 1 upon g j omega is represented in this form, and the magnitude is nothing but this. So we will have the gain margin of a system is equals to 33.6 decibel of your gain margin. So this is how we will able to measure the gain margin of a system. Similarly, we will measure the phase margin of a system. For phase margin, what we have to do, we have to find out the gain crossover frequency. At gain crossover frequency, we know that the magnitude of the system is equals to 1. So substitute that condition omega gc, g j omega gc equals to 1, and the magnitude equals to 1 we put. When we solve this equation, g omega gc we will be equals to 0.125. I will leave it for you. Solve this equation by yourself and verify that omega gc equals to 0.125 or not. At this point, we will find out the value of phase margin, which is equals to 180 minus 180 plus whatever the angle you have. So substituting the value of omega gc, the angle, we will have phase margin of 84.6 degree. So this is for the today's lecture. I will leave a few assignments for you. One, you have to verify that for this particular transfer function, with the help of Bode plot, magnitude and the phase plot, find out and verify that the gain crossover frequency, phase crossover frequency, gain margin and the phase margin are same or not. So take a help of semi-log paper, sketch it and find out. If you have any problem, you can mail me. Thank you very much.